All right, let's start. Good morning. Grades for the first midterm are up. I'm generally happy. The average was around 89, which is pretty high. There are about like 10 or 12 perfect scores. So maybe next time try to make it slightly harder, but we'll see. I'm generally happy. Most of you did compute things properly. Some of you had issues with that angle problem. It was just 180 degrees. So right now, if you go on Canvas and look at the assignment page for midterm 1, you're going to see a key for the first midterm, and certainly you should study it. And if something doesn't make sense, you should contact me and we should discuss it. So we're going to keep moving forward. And in fact, we have our second midterm next week. But at least for the final, certainly it's important that you understand and you're comfortable with the basics of these calculations, row reduction, and so on. Any comments or questions about things in general about the midterm? Yeah, so this week we're supposed to talk a little bit about these abstract vector spaces. I'm going to keep that to a minimum. And I think what I'm going to do is I'm going to try to fold next week's topics into this week, which is signal processing, these spaces of signals, and so on. We still have a couple of things to discuss regarding determinants. I still haven't told you the general sort of like method to compute determinants and so on. We're going to discuss those today. Okay, so just to recap, we were talking about these orientations. Or maybe I should add here too. We had a bunch of rules. For determinant, the most important thing, of course, is that the determinant of the product is the same thing as the product of the determinants. So determinant distributes over matrix-matrix multiplication, insofar as this matrix-matrix multiplication you're trying to do is well defined. That was an important rule. And then we looked at certain special cases of determinants. Namely, if you have a diagonal matrix, then it's the determinant of this diagonal is the product of the diagonal entries. Or if you have upper triangular or lower triangular, I'll just write upper triangular. So this is upper triangular. If you see upper triangular, I don't really care what is happening above the diagonal. You just again look at the diagonal entries. You multiply them. We had this rule. I mentioned it without telling you why. Namely that if you were to take the transpose of a matrix, determinant stays the same. Another rule was matrix is invertible if and only if its determinant is non-zero. If and only if the R number is less than the maximal. I'll write this here. That's also important. I want to discuss determinants of permutations, and that is related to this orientation matter. And once we have that, essentially using this first rule of multiplicativity and these two rules regarding diagonals and upper triangulars or lower triangulars, we'll be able to compute pretty much any determinant. Ultimately, the idea is, well, we're going to start with a matrix. We know at this stage that row reduction corresponds to applying certain matrices from the left, just left multiply. If that is the case, we can start with an A say you're trying to compute determinant of A, then you're going to apply a row operation. One of these, E1. These are all invertible, so you can think of it as E1 inverse E1, A, and then you're going to split it like this. So 1 over determinant of E1 times this. So supposedly, if you started with A, now once you apply a row operation, this is a slightly simpler matrix, and then we're going to do this finitely many times to ultimately get something upper triangular, perhaps, like a reduced form, in which case the determinant is going to be straightforward. So we know these contributions for matrices, for elementary matrices that correspond to scaling, which are these diagonals, or replacing, which are these. Interchange corresponds to permutations, and that's why we need to discuss those also. And even before that, just to recap, I told you that any vector space that is of finite dimension, really, any finite dimensional. So you need to have a finite basis, okay? We're going to talk about examples of infinite dimensional spaces later this week. Any finite dimensional vector space has exactly 2 orientations. And the determinant of a matrix is positive if it fixes the orientation, and negative if it reverses the orientation. The best way to think about these is permutations, because ultimately in the context of row reduction, for instance, you might have negative values here too, but ultimately the main issue ends up being the main complication ends up being because of permutations. So I'm going to look at this. So in the case of R3, we have exactly 3 factorial, that is 6 permutation matrices. Again, I'll write these down. Oh. Identity. And this. And then this. And then this. And then this. And the final one is this one. 0, 1, 0, 1, 0, 0. Okay, so this is diagonal, and I know that the determinant of a diagonal is a product of the diagonal entry, so this is 1. Okay, so that is the easier case. Let's look at this. Okay. Now this matrix interchanges y and z. And so if you start with the standard right-hand roll orientation, meaning you go x, y, z, x, y, z, x, y, z, like this. Okay, and if I were to apply this matrix to it, so this matrix is 1, 0, 0, 0, 0, 1, 0, 1, 0. Now instead of going from x to y, you go from x to z, then to y. So this is the left-hand rule. Okay. Perhaps a better way of seeing this is to visualize the machine learning notation for this matrix. Remember, using the machine learning notation, we would write it like so. I have 3 channels, x, y, and z. And again, x, y, and z. This specific matrix fixes the x channel and interchanges the y and z channels. Whenever you have a cross like this, that's a minus, okay? So that's why it's a -1. Okay. If you want, you can take this as a definition of the determinant of a permutation too, by the way. Does that kind of make sense? Oh, it's really snowing out there. How about this? How would I visualize this? Fix y and interchange x and z. Okay, so this looks like this. Fix y, interchange x and z. Whenever you see one cross, that's a minus. There's one more, this one. Now this fixes z and interchanges x and y. The determinant of this is also minus. Okay. Now, these two are slightly more complicated to see, but the way you should think about it is that both this and this, they have crossings, but they have actually 2 crossings. And when you have 2 crossings or an even number of crossings in general, the determinant is going to be plus. And here's what I mean. So using the machine learning notation, I have this time. First one goes to the second, right? So I'm reading this way. Second one goes to the third. Third one goes to the first. Now, the way you're going to read off the number of crossings when you have a more complicated permutation is by trying to factorize this more complicated permutation into permutations of a simpler type. This, this, or this, where you have exactly 1 crossing. And so, for instance, this I can split like so. Say I interchange these 2, then this has to stay, and then this goes here, so I need to do this, like this. Okay. So what is this? What does this represent? This represents the fact that this matrix can be written as the product of the matrices corresponding to these, but since you're reading the graphs this way, you need to first start with the matrix of this. So this goes there, this goes there. Just look at the table, whatever. Okay. Meaning, you take whatever permutation you have, permutation matrix, you factorize it in terms of permutation matrices that interchange exactly 2 channels, and then you multiply. You say, oh, this interchanges exactly 2 channels, so the determinant of this is -1, and so is this, meaning -1 times -1, determinant of this should be +1. And the same thing works for this one. In a second, I'm going to tell you a much more straightforward way of computing things. This is just the idea, and I'll leave this as an exercise. Take this, factorize it in terms of simpler matrices, and based on that, compute that the determinant of that has to be 1. Assuming that you have this multiplicativity property. Okay. And that's all there is to it in a sense. Because now that we have all of these, this gives us an actionable way to compute determinants of matrices. Now, with 2 by 2, we have this special rule, AD minus BC. There's a special rule for 3 by 3 as well that I think is relatively easy to keep in mind. But for larger matrices, you're going to have to do some more calculations. So I'll give you a couple of different ways of computing the determinant and using different methods. Okay. We'll start with 3 by 3. Initially, I'll use this distribution property explicitly, then transition to the row reduction method, then transition to this special rule for 3 by 3s. Compute the determinant in 3 different ways. So here's my matrix. So this is from the textbook. Okay, in the textbook there's a different method, but I'm not even going to mention this. This is hard to keep in mind. Maybe we'll talk about it later. This is the most inefficient way of computing determinants. And also there's a section in the textbook called the Cramer's rule. It's a certain rule again. Again, this is such an inefficient method that no one actually uses in practice. So I'm not going to mention that also. Because that requires n factorial operation somehow. If it takes n factorial to compute something, you might as well not compute it. So, okay, so this is my matrix, okay? And in the textbook, they tell you that the determinant is -2. Let's try to compute. What is the idea that I'm going to use? Method 1. Well, I'm going to try to essentially do row reduction, but I need to encode the row operations I'm using in terms of left matrix multiplication. And then I'm going to distribute. Okay? So maybe what I can do is this. That's A. Okay. Say I take the first row and subtract twice it from the second row. Okay. Maybe I'll be a little bit more systematic here. That's A. I'm going to have a 3 by 3 here. Okay, so that when I do this operation that I told you, I have something simpler. So do nothing with the first row, do nothing with the third row, but subtract twice the first row from the second one so as to get rid of this 2. So now you have a 0 here. Subtract 10 from 4, you have -6. This is -1. Okay. In terms of matrix-matrix multiplication, I want to come up with a 3 by 3 such that this happens. But when you think about it, I didn't do anything with the first row, so that this has to be 1, 0, 0. I didn't do anything with the third row. This has to be 0, 0, 1. Second row has to be something that corresponds to this operation that I did. Take 1 of the second row and subtract from it twice the first row. So this lower triangular times A equals this. Okay? And if you don't believe me, you can just multiply it to see that this is what happens, actually. And how do you figure this out? Well, that sort of requires some practice, I think. But I know in my head, oh, I have 3 groups of matrices I need to be worried about when it comes to encoding row reduction in terms of matrix multiplication. Lower triangulars or upper triangulars correspond to this replace operation. So I already know what type of a matrix I should get there. Scaling corresponds to diagonal, and interchange corresponds to permutation. Okay, so that's sort of how I imagine it. And then as time goes by, once you get more practice, you end up being able to do this faster. Okay. Any comments or questions about this? Okay. So I want to keep going. So let's call this E1. You see, at this stage, I can immediately say that the determinant of E1 is 1. Okay? Because lower triangular multiplied diagonals, 1 times 1 times 1 equals 1, which means in particular, it's also invertible. Okay? So all these are good. Immediately I can see this from this lower triangular. What else can I do? Well, I can add 3 times the third row to the second to get rid of the 6. So now if I start with this matrix, again I want to have a 3 by 3 multiplied from the left so that ultimately I'm left with this guy. So 5, 0, this is -2, 0, this is -1, and then this is going to be 0. Didn't do anything with the first row, so this is 1, 0, 0. Didn't do anything with the third row, this is 0, 0, 1. How did I operate on the second row? Well, I took the second row and I added 3 times the third row, like this. Need to subtract, I think. Yes. Now it works. Of course, for the purposes of determinant calculation, this plus or minus wouldn't have mattered. Never mind. So this is E2. Okay. Now I keep going. What else can I do? Well, I can scale the second row by -1 and the third row by -1/2. This. So E2, E1A. Again, I'm going to have a 3 by 3 here. And then I'm going to have here 1, 0, 0, 5, 0, and then 0, 1 I want, and then 1, 0 I want here. Okay. Didn't do anything with the first row, so this is 1, 0, 0. Scale the second row by -1, so this is 0, -1, 0. And then the third row I scale by -1/2. Okay. We're almost there. E3, let's call this. I can take this, get rid of this 5. And in fact, I don't even need to do that. What I can do is I can interchange these two to get an upper triangular. That's a good one, okay? Because I know how to compute the determinant of an upper triangular. So let's do one more. E3, E2, E1A. I'm going to have a 3 by 3 here. And ultimately, I want to be left with 5, 0, 0, 1, 0, 0, 0, 1. Interchanging these two. Didn't do anything with the first row. For the second row, take the third row. Okay? And for the third row, take the second row. Okay? So, all this is sort of like a faster or, more explicit way of doing row reduction in a sense. I kept track of my row operations in terms of matrices, but I have a matrix equation. A4, A3, A2, A1, A, these 5 matrices when multiplied gives me this. I know that each 4 of these is invertible. Permutation, diagonal, upper triangular, lower triangular, these are all invertible, and I know how to compute their determinants. So I can send them to the other side. A is, let's call this U. You got to be worried about the orders. Because E4 is to the left, you need to first multiply with the inverse of E4, and then with the inverse of E3, and so on. I have this equation now apply determinant, distribute. Since I know that determinant of AB equals determinant of A times the determinant of B, well, I can just distribute all of them. And in fact, what I can say also is that determinant of a matrix inverse is going to be the reciprocal of the determinant of the original matrix. Maybe I should have written it over here, perhaps. Determinant of A inverse is 1 over determinant of A. So determinant of A is 1 over determinant of E1, 1 over determinant of E2, 1 over determinant of E3 times 1 over determinant of E4 times determinant of U. Okay, now we look. Determinant of E1, what is it? One. Determinant of E1 is 1. Why? Because lower triangular, 1's on the diagonal. Just take the product of the diagonal entries. Okay, this is 1. What is the determinant of E2? Also 1. Now it is upper triangular. I don't care. Insofar as you have triangular, multiply the diagonal entries. What is the determinant of E3? Well, minus 1 times negative 1/2 is plus 1/2. Yes. So this is 1/2, but you need to take the reciprocal, so it's going to contribute to 2. And you see, this is a permutation. It interchanges exactly 2 channels, so the determinant of this is minus 1 also. And finally, U is upper triangular. Its determinant is 1 again. So you multiply everything, that gives you minus 2. This one is dead. Which is what the textbook says also. Okay. This is method 1. Any comments or questions about this? Yes?
I think I'm not following quite my calculation. Since the determinant of A would also be the determinant of the right-hand side.
Yes.
But then we get determinant of the inverse of E1,
Exactly.
correct?
Yes.
Would be then 1 over.
Yeah, here's the rule that I added. So why? Because I know that the determinant of the identity matrix is 1. It's a diagonal matrix with 1's on the diagonal. But identity is the same thing as any invertible matrix multiplied by its inverse. Insofar as the inverse exists, of course. But if that exists, I can just split it like so. And so that determinant of matrix inverse is the same thing as 1 over the original matrix. That's what I used here. Very good. Any questions or comments about this first method? Now, this method is useful, perhaps at more upper level considerations. What you can do is you can bypass some of the considerations here. Essentially, you can basically cut the middleman. Instead of first factorizing A into a bunch of matrices like this, well, you can just keep track of what sort of operations you're doing, and based on that, adjust your determinants. Okay? So this is method 1. I'll do method 2, using the exact same row operations, because we know there are multiple different ways of row reducing. I'm just going to use the same ones to see how one can sort of shortcut. Now, when you're scaling a row, well, you need to just take that constant out, because that is the effect of applying a diagonal. When you're replacing, you get to do that for free. When you replace as a row operation, the determinant doesn't change. Okay? That corresponds to the fact that lower triangulars and upper triangulars with ones on the diagonal, they have determinant 1. So, and in fact, instead of writing determinant of A, you would also see this notation, A in absolute value, pretty much. Okay? I'll just use that notation. It's much more convenient sometimes. 5, 4, minus 2, 0, minus 1, 0. Instead of writing determinant, I'm going to put bars, absolute values. This is also in the textbook. This is the notation for another notation for determinants. So what did we do? In the first step, I took the first row and subtracted twice it from the second row. This, in terms of determinants, costs nothing. So I can just write it like so. Then minus 6, minus 1. Okay. I just fast forwarded this idea that, oh, there's a left multiplication, whatever, but when I do this row reduction, it's a replacement operation, which means that when it comes to determinants, determinants should not change. You just like bypass all these matrices, whatever, do simple row reduction. Okay? Now we keep going. So maybe I should mark these. So this is this step. Now I keep going. Now you see to go from here to there, what I did was I took this and added or subtracted 3 times it from the second row. Again, determinant is not going to change. Zero, 0, minus 1. Okay. And in fact, this is also useful because if you're at this stage, if you're only worried about computing determinants, you don't even need to worry about this number. Right? So here we had to write this minus 3, even though it wasn't going to matter ultimately. Well, you can just say, I'm just going to take this minus 2 and knock this minus 6 out, and I can just say it's 0, pretty much. I just get to pretend that this minus 6 is a 0 for the purposes of calculating the determinant. Okay, so I keep going like this. What did I do after that? Okay, I did a scaling. Okay, so when I scale, now I need to adjust the determinants. So it's almost like this. I didn't do anything with the first row. When you have a scalar in one row, you get to take that out of the determinants. So imagine 0, 0, minus 1 is nothing but minus 1 times 0, 0, 1. Take the minus 1 out. And likewise, take the minus 2 out. This is step 3. Okay. And then when you have an interchange, you pick up a minus. Minus 2 times 1, 5, 0, 0, 1, 0, 0, 0, 1. At this stage, you can say, oh, this is upper triangular with ones on the diagonal, so this determinant has to be 1. We can do it this way too. Oh, so I should have said, I guess, this is step 4. Okay. These two are pretty much the same idea. One of them is where you use these row reduction matrices explicitly. The other one, you just record their effects in terms of determinants. Okay. But it's the same calculation or computation. Consequently, either one of these methods are going to work for any n by n. Okay? Doesn't need to be 3 by 3. In a second, I'm going to give an example to that as well. But before that, I want to give you sort of like a shortcut that works only for 3 by 3s. Any comments or questions so far? Okay. I'll erase, well, I'll just do it here. Here's the third method. That works for 3 by 3s only. So I should record this. This works for n by n. This works for n by n. Method 3 is only for 3 by 3s. And it's kind of mysterious in a sense. Take your matrix. Okay. So this third method has to do with these channels underneath somehow. But you do it like this. Let me record it here. Okay. 1 to 0, 5, 4, minus 2, 0, minus 1, 0. Maybe I'll give you a fourth method too, actually. So, determinants. I'm going to write this twice so that you see what is happening. Okay. And then, so like this. These are not determinants yet, okay? Just setting up a notation here. So, for this part, I'm going to combine, I'm going to choose certain certain triples of entries and multiply them together. These are always going to contribute positive, and these are always going to contribute negative, and that's why there's a minus. And you start drawing triangles this time. For the positive contribution, this, meaning, okay, 1, 4, 0. 1 times 4 times 0. Then this triangle, okay, 5, 0, minus 1. Then this triangle, 2 times minus 2 times 0. Okay, these are the positive contributions. They're all 0, of course, but never mind. For this, you do it the other way around. You look at the off diagonal, and then the two triangulars that correspond to it, this one and this one. So this is the positive minus 0 times 4 times 0. Then, 1 times minus 2 times minus 1. Then 5 times 2 times 0. Okay. 0, 0, 0, 0, 0. That's a plus 2, but with a minus, it gives you minus 2. You can do it this way as well. This only works for 3 by 3. Just to draw it better, Okay. So plus contributions are like this. Okay. You multiply the entries. Multiply diagonal entries, these 3 entries, these 3 entries. These give you plus. The other ones, they're going to contribute a minus. So you start this way, multiply this, 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 then this, 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 and then this, this, this. If you're good with calculating on the go, this is actually very convenient once you get used to it. Especially for calculating curls and stuff too, if you know multivariable. Just by looking at things, sometimes you can compute. Okay. That's how we do it. I'll give you yet another method for, again, 3 by 3s. It's essentially a variation of this. So I'll give it as an exercise as to why this works. I'm not going to tell you. Why does this work? The method 3. Method 4, again for 3 by 3s only. Well, people came up with methods for 3 by 3 because, typically multivariable calculus is in 3 dimensions. So, and these determinants end up being very useful, in fact. Cross products, curls, and whatever. So people came up with a lot of different methods. So if you're trying to compute this, okay. Now, it's essentially the same method as this other one, as method 3, but instead of looking at triangles, you basically unfold. What you do is, well, you duplicate the first 2 rows, or first 2 columns, it doesn't really matter. Let's just take the columns, in fact. Write it like this. Okay. Or maybe I should have used a different color, in fact. I'll use a different color. I'll use green. 1, 2, 0, 5, 4, minus 2. You put the first 2 columns, sort of duplicate them, and then there's a plus contribution and the minus contribution. Plus, 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 and then the other 3 give you minuses. That's a minus, that's a minus, that's a minus. So basically it's these triangles but unfolded so that you have only lines instead of triangles. Okay, let's perhaps have a look. If you multiply these, that's a 0. Multiply these, that's a 0. Multiply these, that's a 0. Same zeros over there, in fact. Then I look at it this way. This gives me 0. This gives me 1 times -1 times -2 is plus 2. Okay, and that's a 0. But this has to be this contributes with a minus, so the determinant is again -2. Okay, you can do it this way. If you want, there's a 5th method where instead of using duplicates of columns, you put duplicates of rows. You do the same trick this way, that way, whatever. Compute gives you again the determinant. Okay. These are pretty much all the methods I know, I keep in mind when it comes to determinants. Perhaps the 5th method that could be useful is, or the 6th method, I guess, useful for n by n's is this recursive method. I have a couple minutes, so I might start talking about it. So here's an example here's a large example. It's a 5 by 5. Like this. -7, 2, 0, 0, 0, 8, -5, 1, 2, 0, 9, 7, 5, 4, -2, -6, 3, 0, -1, 0. So 5 by 5 this time. My intuition would be, I wouldn't be using this other method in general. My intuition would be to try to turn this into an upper triangular. Because somehow when I look at this, I say to myself, well, these two entries are the contentious ones. And in fact, let's sort of, even before giving this new method, let's try to sort of figure out what we can do. When I see this, thinking of this second method, I immediately look at the fifth row. Because this is a very nice row, you see. Only one of the entries is non-zero. I can take this, get rid of all of these entries. Okay, that sort of like simplifies. When it comes to determinants, again, the name of the game is trying to get as many zeros as possible. I'm thinking, is there anything else I can do? Yeah, let's just start with this. Now I'm looking at the determinant. This determinant is the same thing as take this 3 out. Oh, I guess we didn't talk about that, but we can certainly take this -2 out. And then 3, 0, 0, 0, 0, -2, 0, 0, 0, 0, 8, -5, 1, 2, 0, and then 1, 0, 0, 0, 0, -6, 3, 0, -1, 0. What did I do? At once, I took this and I got rid of these entries. I know that because all other entries are 0 in the fifth row, I don't need to change the other entries. I can just duplicate. So I have a bunch of zeros now. And on top of that, I took out this -2. Okay. I want to finish this calculation. I want to take my time doing this. I think it's a good place to stop for today. We're a couple minutes early, but I think that's okay. Thank you. All right, let's start. Good morning. Well, thank you for being here. The weather seems to be getting worse, but I appreciate you showing up. So today I want to keep doing a couple more examples of determinant calculations. I want to discuss one more method. I think in the textbook it is called the cofactor method. And indeed, in the first midterm, some of you did use it to verify that this given matrix is invertible. They just computed the determinant using this cofactor method. I would not recommend it, to be perfectly honest. It's not very efficient, but it's in the textbook, so we might as well kind of discuss it. It's one of the sort of classics that they teach you. So here's this 5 by 5 that we had started thinking about, and its determinant is -12 apparently. Let's try to compute it. I'll just try to do this row reduction thing. Row reduction in general is you're going to be able to conclude or compute the determinant faster with row reduction. Okay, so this time let's say method A, so the row reduction method, row reduce. fact, I'll do one more row reduction in a second because I computed something else, or something reduction, column reduction, let's say. So you take this and then you do all the shenanigans. So like this, minus 7, 2, 0, 0, 0, 8, minus 5, 1, 2, 0, 9, 7, 5, 4, minus 2, minus 6, 3, 0, minus 1, 0. Remember, when you put these absolute values, that represents the determinants. It's fairly common notation. So when I look at this, immediately I realize, well, the fifth row has only one non-zero element, one non-zero entry. So I can use that to knock these ones out with no cost of changing the other entries, because everything else will be fixed. Okay? And then, for instance, I say, oh, the third row has exactly 2 non-zero elements, so that's the second best. Hey.
I cleaned the whiteboard.
Thank you.
Tomorrow is Thursday. We're getting close to Friday.
Oh, yeah.
Have a good day, everybody.
Thank you. So I take this. And remember, we could also scale. And when you scale, you need to change the determinant appropriately. So when you take this 2 out, or minus 2 out, you have this. And simultaneously, I can get rid of every other entry in the same column. Minus 2 times like this, minus 7, 2, 0, 0, 0, 8, minus 5, 1, 2, 0, 1, 0, 0, 0, 0 here, and then minus 6, 3, 0, minus 1, 0. I did 2 things simultaneously. Okay? On the one hand, I scaled the fifth row by minus 2, or by 1 over minus 2, whatever. So you just pull out that constant. That's a number. And then you can just use this and do replace operations to get rid of all of these entries. But you see, now that I have this, I can likewise take the third row and get rid of other entries with no cost on the determinant level. So this is 0, 0, 1. Oh, that's a 0. 0, 0. And then 0, 0, 0, 0, 1. And then minus 6, 3, 0, minus 1, 0. Well, I guess I didn't even need to do that in a sense. All I needed to do was perhaps to get rid of this 2, but never mind. This is certainly perfectly valid. What else can I do? I can take this one and get rid of these 2 entries, and then I can take the minus out as well. So this is 2 times 3, 0, 0, 0, 0, minus 7, 2, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. Did that. Okay. Take another 2 out. Get rid of this minus 7. And then take a 3 out. So that's 12. Um, 0, 1, 0, 0, 0. And then 0, 0, 1, 0, 0. 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. Now that's a permutation matrix. And I know if I interchange once, I pick up a minus. But if I interchange fourth and fifth, I get the identity matrix. So that's minus 12. Okay. If you're trying to do this faster, you probably would not be writing all of these steps. What you would do is something like this. Well, I'll write it on the side. Because you don't need to keep writing the matrix over and over if you're just like trying to compute something like this. 1, 2, 0, 5, 4, -2, -6, 3, 0, -1, 0. Say you start like this, and you're trying to compute, okay? Compute this determinant. Again, going through the same motions, you would say, okay, I'm going to take this, take that out, get rid of these guys. Now these are all zeros. Times. You don't write it. You keep going. Now that this is 0, you can take this, get rid of these. So this is 0, 0, 1, 0, 0. It's like this. Then you can take this guy, get rid of these ones to pick up a minus. Now this is a plus. Well, these two give you 6. And then if you were to flip the orders of these two, that gives you yet another minus. So 3 times 2 minus 2 times -1. That's another way of computing -12, which is essentially the same calculation, except that you don't do this like step by step. You just look at the matrix and do it on it, essentially. This is row reduction. So what are the benefits? Typically, this is going to work faster than any other method. This is the fastest method. Like this is like an algorithmic statement. But the trade-off is that you need to be aware of the sort of structures. You need to know, oh, I can use this row, this column, whatever. So that you sort of cancel out certain things so as to get something that is easy to compute, for instance, in this case. Okay. Any comments or questions? Now, method B is this cofactor method, and it's a recursive sort of idea. Okay, I'm going to erase this. This is a new method that I didn't mention yesterday. In my opinion, there are more things to keep in mind to perform this cofactor method properly. I would recommend that you just stick to this row reduction method. Works perfectly well with things that you've been doing since week 1. Method B, cofactor method. This works for any n by n. Okay. First, you need to know the size of the entries. Okay. If you have a 3 by 3, the signs are like so. Always at the top left corner, you start with a plus, and then you alternate between plus and minus. So this is plus, this is minus, this is minus, this is plus, and so on. Okay? These are the distributions of pluses and minuses. We're going to add and subtract a bunch of things depending on these things. It's kind of mysterious how this actually works. If you have 4 by 4, again, top left, always plus, and then you alternate. Okay? I'll do one more. 5 by 5. Top left, you start with plus, and then alternate. Okay. The idea is this with the second cofactor method. It's a recursive calculation. You say if I'm trying to compute the determinant of a 5 by 5, well, I'm going to write that 5 by 5 determinant in terms of 4 by 4 determinants. And those I'm going to write in terms of 3 by 3 determinants. What you do is this. You start with your matrix. You pick one column or one row. Okay? It doesn't matter which one. Typically, you would choose a row or column that is convenient. So for instance, when I look at this, it seems like choosing this column is going to be convenient. Do I want to do it like that? Yeah, let's do it like this. So you pick one of the columns or rows depending on the shape. Say you picked this column. And so you're going to expand the 5 by 5 determinant along this column. And this is what you do. I'm going to write everything again. Nine, 7, 5, 4, minus 2, minus 6, 3, 0, minus 1, 0. I'll pick it with green, actually, because we're using pluses and minuses. We're using blue with plus over there. Pick this one. Now, take this. I'm going to expand along this column. You write each of these entries, and then you add and subtract depending on these pluses or minuses. Meaning, what you do is this. So minus 0, plus 0, minus 0, plus 0. Okay? These are all numbers, and each of these you're going to multiply with the remaining 4 by 4. What do I mean by that? Next to 3, okay, you burn the same row, and you're always burning the column you chose. Now you're left with this 4 by 4. And so next to 3, you're going to have the determinant of that 4 by 4. This is not at all intuitive as far as I'm concerned, and that's why I'm doing it the last. The rest are always going to be 0 for this specific case, but just to reiterate, let me write these. This, okay, I look at it, oh, this is a minus. So I take this, okay, this 0 goes there, and from there I look at this minus, and therefore next to it there's a minus. Okay. Now burn the column and the row this specific entry belongs to. Okay. So this is gone and this is gone. You see, you again have a 4 by 4. Now you put here the determinant of that 4 by 4. Burn the second row, then you have this. This is not pleasant, okay? You just need to know this. Any comments or questions about this so far? Now you keep going like this. Take this, say plus minus plus. Now that's going to have a plus. Put 0, burn the row, this. That's going to give you another 4 by 4 determinant, and so on. I'm not going to write these because, as you see, ultimately you're going to multiply these with 0, so these are not going to count. That's why we chose this column. We said, oh, this is a nice column. So, in any event, we're done with all this. So now you look at this and say, okay, I'm going to apply the same rule recursively to this guy. Okay, just to have some change. Let's this time take. Well, I mean, I'm kind of scared to take a different row. I want to take the, again, first column here. Okay. Three, open paren, 2 times, okay, burn this. This is a 3 by 3. Okay, minus 0, plus 0, minus 0, nothing else. So I'll just write it like this. Okay. Now at this stage you can use one of the rules for 3 by 3s, or you can still keep going with this cofactor method. This is small enough for me to do it. I mean, what you can do is you can use this third column. For some change, let's try to use this guy. Okay. So now I have 6 here, open paren. 1 minus 5 plus 0. Okay. If I burn the 1, I get 4 minus 1 minus 2, 0. If I burn the 5, I get 2 minus 1, 0, 0. And then if I burn the 0, I get 2, 4, 0, minus 2. At this stage, you can use AD minus BC, or keep going with the cofactor method, choose one of these rows, whatever. I think at this stage, it's good to just fast forward this. This is 0. Oh, this is 0. What is the determinant of this 2 by 2? Negative 2. AD minus BC. Minus 2, minus 12. You can do it this way too. Yeah, the mysterious thing here is that, like, for instance, if I were to choose the first row and like inflict pain upon myself, you can still do the same thing, okay? And somehow, at the end of the day, you would get the same number. Somehow it doesn't depend. It doesn't matter how you, which rows or columns you end up choosing. They always give you the same thing. Okay. Again, it's hard to keep in mind. You need to be worried about pluses and minuses. Experience shows a lot of students like using this method, but often they mess up the pluses and minuses. It's I would just recommend just stick to row reduction and know that, oh, lower triangular, upper triangular, whatever. It's much more safe, I think. And in general, it's going to conclude faster. You're free to do whatever you want, of course, as long as you can compute. Okay. Comments or questions? I just got a flashback. We learned this stuff. So I'm from Turkey, and in Turkey they teach you calculations with matrices back in high school. And I remember we would have these like 5 by 5s all non-zeros, and you're not allowed to use any row reduction and compute the determinant. I remember doing this like pages after pages, with like nothing cancels out. I guess that's how you learn. Okay, I'll do one more way, and in fact, I'll introduce a different idea, slightly different idea. So far, we've been using row reduction, but in fact, you can do column reduction as well. If instead of left multiplying by elementary matrices, you right multiply your matrix, that corresponds to column reduction. Okay? Left multiplication corresponds to column reduction. Okay, so you can do both in tandem. I told you that the determinant of a matrix is the same thing as its transpose, so you get to both do row and column reduction simultaneously, or in an alternating fashion. So here's method C. This is like a complete or full reduction if you want. Both row and column reduction. I'll erase this. This. Okay. So method C, column and row reduction, or row and column reduction. Okay. Now, you see, again, I can use this -2 to get rid of these 4. Then I can use this 3 to get rid of these. Then this 2 to get rid of these. And then I can pull everything out. 3 times 2 times -2 times something. 1, 0, 0, 0, 0, 0, 1, 0, 0, 0. That's a 2 at this stage. In one step. Use this. Take the scalar out and simultaneously get rid of these. That's a row reduction. Use this. Take the scalar out and simultaneously get rid of the same entries in the same row, and likewise this guy. Okay, and that's what you're left with. But then, of course, I can safely replace this 2 by 0, row reduction, and then there's a minus there. So if I flip and get rid of the minus, these would cancel out, and ultimately this would have determinant 1. Which means I have -12. We can do it like this too. Okay. Any comments or questions? Yeah.
Wait, how does that work if the 2 is still in there?
Well, I can take this and get rid of this. It's a replacement. It's not going to change the determinants.
Okay, I see.
So I'm saying, oh, I'm going to pretend it's not there anymore. Yeah, if you plug in a matrix on Wolfram, for instance, you're going to see sort of like a color map or heat map type of a thing. That's why, so there's a reason why, because somehow you would like to be able to just look at the entries and sort of detect some sort of pattern. Essentially, we've been using the same idea over and over. It's like, if I have a row with exactly 1, 1 and all else 0, that's a very good row, right? I can just knock a bunch of entries out using that. So it requires some amount of finesse, of course, but you know, that's why you're taking this class. Okay, that's all there is to it. Okay, let's do one final example, and then we'll switch over to vector spaces. It's a 4x4 this time. -5, -6, 4, 9. Okay.
Quick question.
Yeah.
Is this another method or is this just an example?
Just like a general example. Like I said, it's like it doesn't matter which method you use insofar as you can compute this determinant accurately. I'm going to try to do the row reduction method until I see some patterns, okay? Right now I don't see any patterns, so I'm just going to go ahead with row reduction, okay? When I see a matrix, that's pretty much like the third thing I do, right? Like I look at the number of rows and columns. What is the third thing? Start doing row reduction so that you have the R number too. Okay. Yeah, so for instance, if I add twice the first row to the third row, that would be 3 in terms of determinants, and I would be able to knock out this -6. Zero, 5, -3, -6, and then the fourth row stays as is, like this. Here I have a 0. I'm adding twice this to this. So -2 plus 7 is 5. 4 minus 7 is -3. -10 plus 4 is -6. Okay, I have 2 rows repeating. Our number is less than 4, maximum possible, which means this is not invertible, which means that this determinant is 0. Okay. So rank is less than 4. Invertible if and only if rank is maximum possible, if and only if determinant non-zero. Okay. If you don't catch that, well, you would keep doing the row reduction, okay? Ultimately, things would cancel out and you would end up with a 0 again. But certainly, it is more preferable for you to look at this 4x4 at this stage and realize that R number is less than 4, and therefore it is not invertible, and therefore that determinant has to be 0. It's better to do that. You don't want to calculate things, right? You want to calculate it as little as possible. But if you end up not seeing it, well, you can just go ahead and run one of these algorithms, and it's again going to compute for you 0. Any comments or questions? Okay. So vector spaces. This is where the more advanced and pure mathy version of this class starts at this next chapter. You define what it means for something to be a vector space axiomatically, and you develop everything based on those axioms. Obviously, we're not going to do that, but I think it would be a good idea. It would be a good thing for you to be exposed to these axioms at least once. Once I give these axioms, we'll focus on certain applications. Certain vector spaces that satisfy the axioms that still are not of the types that we've seen so far. So this is chapter 4 now. While we think about what is happening in a vector space, we have a fair amount of experience at this stage, and we have some examples. Tuples are n, right? That is one example. Another example is a space of matrices. That's also a vector space. Another example is, well, if I have two vector spaces in a linear transformation, or rather the space of all linear transformations between them itself is a vector space. So what do we need? We need two operations. We need a vector addition, and we need a scalar multiplication. And for scalar multiplication, we actually need to first determine what a scalar is. Okay? It turns out that there's a abstract mathematical sort of object called a field, or more generally a ring, that can act as a field of scalars, or the set of scalars. So a field, okay, I'm going to denote it like this. It's like R, but instead of writing R, I write F, is a set with addition, subtraction, multiplication, and division. Similar to reals or complexes or rational numbers. Okay, so here's examples. So reals, C, complex numbers, Q, rational numbers, there are more. Some people, or under certain circumstances, you sort of drop this division, and that gives you what is called a ring. So for instance, integers, you have like addition, subtraction, multiplication, not necessarily division. If you divide two integers, you may end up with something that is not an integer, but still you can do linear algebra using integers only. Let's not get there. Here's a nice, interesting example. B, binary numbers. Well, just to give you an idea, so numbers like pi is in this space of reals, or field of reals. It is not rational. So rationals are just ratios of integers, complex numbers, x plus iy type things, which you've seen in a previous problem set with the Pauli matrices. Binary, well, it has only two elements, okay? 0 and 1. So this is the field of bits, if you want. How does addition work? Well, works like this. 1, 0. The only difference, of course, is that when you add 1 to 1, you say, in this world, 1 plus 1 equals 0. Okay. For bits, that's what you say. Okay. And then how does multiplication work? It works as expected. can also think of these in terms of like logic gates or electrical circuits, whatever. Let's not get there. You take one of these systems with 4 operations like this, and you say, oh, this is going to be my field of scalars. I'm going to sample my scalars from this set of numbers, so to speak, or more complicated things. Then a vector space over your field F is a set that has that is endowed with 2 operations, addition and scalar multiplication. For F, a field, a vector space V over F. Don't worry too much about these definitions and whatever. Clearly, the point of this class is not axiomatics, whatever, but just mentioning these for sort of general purposes, common sense, all that stuff. But obviously, I'm not going to ask you things about these axiomatics. But it's good exposure. Vector space V over F is a set together with 2, let's say, functions vector addition is going to be one function that depends on 2 vectors, gives me back 1 vector, and scalar multiplication is going to depend on, again, 2 things, 1 scalar and a vector, and it's going to give me yet another vector. Okay. Alpha, let's say, for vector addition. This notation means, well, alpha just, you plug into vectors into alpha, it gives you back 1 vector that is supposed to be the vector sum. And sigma, 1 scalar and 1 vector, you combine and it gives you yet another vector, satisfying certain axioms. Okay, let's pause. Try to figure out or abstract out what sort of axioms we should have. And of course, if you see in this notation alpha of V1, V2, this should be pretty much V1 plus V2. And sigma C comma V should be C times V. It's just that this plus you're trying to define, and so you cannot just write it like this. So what sort of properties does addition have? Just look at what is happening in Rn. Okay. Well, it's kind of silly to write these things, but this is how you sort of abstract out the axioms. You have this, for instance. So if you're trying to add 3 vectors together, it doesn't matter in which order you add them, in the sense that you can first add the second and third, and then to the end result you can add the first, or you can do it the other way around. That should be the same. Try to remember what else. Well, certainly for vector addition, the order should not matter. Before that, well, we have a 0 vector. Okay, 0 plus V is V. So you need to say that there's a vector like this. And then if you add 2V, something called minus V, it should give you the 0 vector. Again, you need to axiomatize this one. And finally, you need to axiomatize the idea that v1 plus v2 should be the same thing as v2 plus v1. Okay? These are the properties, and you write everything in terms of alpha. So 4 properties, I can just write it like this. So for instance, the first one in this alpha notation would look like this. Okay, what does it say? On the left-hand side, it says add v2 and v3 first, then add v1 to the end result. Okay? So this this expression over here, in the more intuitive setting, in the abstract setting, would look like this. Okay? And then you do it the other way around. First, you need to add v1 and v2, and to the end result, you need to add v3. And so you need to, axiomatically speaking, you need to force alpha to be a function that satisfies this equation. Okay? This is how you sort of axiomatize things. Then you say, well, there's a vector. Let's call it zeta for 0. So there's an element zeta in B such that for any B in B, alpha V comma zeta is V, which is the same thing as alpha zeta comma V. Okay, instead of plus over there, you see I'm using this alpha notation, and instead of 0, I don't want to call it 0, I'm just calling it something else, zeta. And instead of writing V plus 0, I write alpha of V comma zeta. Okay. Then what do I need to say? For each V, there is V bar, let's say, such that when plugged into alpha gives me zeta. There is a, let's say, V bar in B such that alpha of V comma V bar is zeta, which is the same thing as alpha of V bar V. And then the order should not matter. Alpha of V1, V2 should be the same thing as alpha of V2, V1.
Sorry, what's the word alpha? Oh, that's any, for any.
Yeah, for any. Sorry. So these 4 axiomatize for me how vector addition should operate. I'm going to say more things about how scalar multiplication should operate, and then I'm going to connect the two, okay, some distribution properties. So the version of this class that is for pure math people like me back in the day. So you start with these axioms, and from there you would just like prove a bunch of things. So for instance, you just assume this, and from this you derive that in any vector space there's a unique zeta like this. And for any V, there's a unique V bar that is the additive inverse and so on. Okay. Going back, now I want to figure out some properties of the scalar multiplication that is only about like multiplication. So for instance, I have, well, C1, C2 times V. I can just multiply 2 scalars. That gives me yet another scalar, and then scalar multiply the vector. Or I can do this in series like this. Okay. Oh, I need a scalar number 1. So C times 1, or maybe I should say 1 times v is v. Okay. I think these two are sufficient. Yes. And so you would write sigma of C1, C2v is the same thing as sigma of C1 applied to sigma of C2v. This corresponds to this. And then you have this. And then I want to add some distribution properties. I should be able to add two scalars and then distribute and so on, so that C1 plus C2 times v should be the same thing as C1v plus C2v. And C times v1 plus v2 should be CV1 plus CV2. So these are how alpha and sigma interact with each other. This is the left-hand side of this property. This should be the same thing as alpha sigma C1v sigma C2v. And then finally, we have sigma C comma v1 plus v2 is alpha of sigma C v1 comma sigma C v2. And I think all these are, this is all there is to it. Maybe I'm missing one, but this is the general idea, okay? I'm not going to ask you to prove x, y, z using these. This is just general exposure. What we're going to do on Friday is we're going to look at specific examples of more general vector spaces compared to the ones that we've been accustomed to so far, okay? Thank you. I'll see you on Friday. All right, let's start. Good morning. I'm going to take attendance today. So we have our second midterm scheduled next Friday. I'll release a guide for it later today. And P-Set 4 grades also. I'm done with my part, but I'm still waiting for the grader to finish their part. So we were talking about this axiomatic definition of a vector space. We started with a field, and then we took that set of numbers where there are certain numerical operations or metaphorically numerical operations, and we defined a vector space on or over that field. Now, I told you I'm not going to ask you to do anything with these axioms, whatever. But still, I thought it would be good to at least have a sense as to what type of things people are interested in or people look into. If you're into this axiomatics brain rot, you can look into this web page called NLab. You can go to town. Every single sort of item in that list has been analyzed to the limit. People still find some relations between things, but still, everything has a name, generalizations, whatever. not going to go beyond that. For us, two things that are the consequences of this more axiomatic approach is, well, one of them is we can talk about more complicated or perhaps different looking vector spaces that we haven't seen so far. This turns out to be rather important for applications. Important examples from applications. That's the first. And then the second consequence, in fact, is this observation that in the axiomatic approach, we in fact didn't define a basis. So somehow the notion of a basis really is something you put on top of the vector space. We sort of deduce the existence of a basis and so on. In the axiomatic case too, you ultimately essentially assume once you need to use a basis, but to say the least, in the basic vanilla definition of a vector space, you don't really define the notion of a basis. There is a different field, somewhat adjacent, where the notion of a basis is axiomatized, and that is what is called the matroid theory. It's like matrix, but you so call it oid, matroid. Matroid theory for, I'll write it somewhere else actually. I don't want to confuse. So, axiomatic study of the idea of a basis matroid theory. If you're into combinatorics and stuff like that, it might be nice to look into this. And even in applications, it seems a lot of people are finding some use in biology and stuff. Somehow they have this idea of independence, but they axiomatize everything, and then they get to sort of apply this idea to different situations. The second thing, let me finish what I was saying. The first implication is important examples. Second implication is, well, the fact that the notion of a basis is not part of the axiom set for a vector space means ultimately that somehow we should be able to talk about things in a basis-free manner. And this is the starting point of what is called relativity. If you're familiar with physics, you would want to say something like, oh, the laws of physics are independent of the inertial frames under which you're observing those laws when you're doing an experiment and whatever. Meaning, for instance, if you have sort of like a wedge, this is like a classical physics problem. There's like a barrel, let's say, and there's a G, the gravitational force. Okay? So you would sort of put a coordinate system like this, or maybe like this, whatever. You would split the forces in whichever you want. Maybe there's like friction, all that. You can use whatever coordinate system you want, and certain coordinate systems might be helpful in terms of calculating things, but not for the final answer. Okay? So physics, reality is independent of the inertial frame of reference. So what physicists call an inertial frame of reference is basically a basis. It's slightly more complicated than that, but for now we can just take it that way. Which means that somehow we need to be able to think about things that we've been doing without necessarily referring to a basis, or from a different perspective, we need to be able to figure out what the effect of changing a basis is when it comes to certain representations. So in the textbook, you'll see a section regarding change of bases. There are things like change of basis matrix and stuff like that. And so I thought, and that is kind of confusing. And even though we will cover this change of basis stuff before the second midterm next week, I would rather have you at least one problem set and do some calculations before the midterm. So for the second midterm, this change of basis stuff is not going to be included, okay? Because it is really confusing. It can be really confusing. So relativity in the textbook, this is the change of basis. So in the guide too, I'll write it. No change of basis. I might give you certain examples in the exam that are perhaps more complicated than Rn, but even there I'm going to be rather limited. I'd rather have a problem set at least so that you can talk about it. But of course, the trade-off is that change of basis is going to be included in the third midterm. Okay. So, examples of vector spaces. Let's just take our time, come up with some nice examples that are relevant in applications. Let's first use this, in fact. B. Just fixing my field to be the binaries. So this is the binary field. Okay. It has only two numbers in it, 0 and 1. Everything as usual, except that 1 plus 1 is 0. That's your new rule in this field of scalars. So this is what is called characteristic 2. There are other characteristics and whatever. There are many other fields, but let's not get into that. This certainly is very important for computer science stuff, information theory stuff, and so on. Here, for instance, if I were to look at B3, okay, this is the so-called three-dimensional binary vector space. Yeah?
Would we define 0 plus 0 as 1 as well?
No. 0 means when you add it to something else, that other thing has to not change.
Okay.
Yes. So 0 plus 0 is 0. So every other thing is as usual, except that 2 is equal to 0. Yeah. So this is the space of, this is the three-dimensional binary space. But you can also think of it as the space of 3 bits. Like one dimension here gives you 1 bit. Maybe I should say 3-bit codes, blocks, better perhaps. Code blocks. Huh. So you see, the rules, even though certain sort of linear algebra rules are the same, the intuition is very different here. Because this space has exactly 8 vectors in it. Very bizarre. And so you can just list this down. Right? So 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1. This vector space has exactly these 8 vectors. Okay? And in fact, people would draw this as well. And so how can I draw this? Well, I'm just going to draw a cube, and the vectors in my B3 is going to be just the corners. Okay. Exactly 8 vectors here. What's the point of, perhaps I can do this, again, x, y, z. So for instance, this here is 0, 0, 0. This one is 1, 0, 0. This one is 1, 1, 1. And so on. What is the benefit of doing this? Well, first of all, you can do pretty much all of what we did so far. Look at matrices, look at equations, do row reduction using only 0 and 1. Do everything. Bases, all that stuff. So for instance, you see, this, again, is a basis. It's three-dimensional. You can kind of use the geometric intuition that we've been developing so far. Another thing, too, is that once you can imagine this space of 3-bit code blocks, well, if you imagine them like this, you can think about what the distance between any two vectors is. And using that idea, you sort of develop it further, and you turn it into error detection and correction, for instance. Okay? And sort of different vectors. So I'll just write something very short. So what you would do is something like this. You would encode whatever message you have into some large space, sort of turn it into zeros and ones. And it turns out, say, your total message has n bits. In other words, that n-bit message is one vector in this vector space. And it's somewhere here, let's say. This is your message. Okay. Now you look at sort of nearby vectors in the space of n-bit codes. And ultimately, error correction would require something like this. Say you have your message. You encode it. Now you have a vector. You're going to send it to something. Okay? Now it is received. But you're expecting that there's going to be some noise. Okay? Even though you started with this pristine message, because of the, because of certain things that people look into in information theory, the message received probably is not going to be the same as the message sent. But you come up with algorithms, certain sort of procedures that allow you to say, oh, if the message I received was this, somehow you encode a certain algorithm in the message itself, which allows the receiver to correct what you actually said. Okay? What the actual message was. Does this kind of make sense? I'm being sort of like super vague, of course, but this is like a different class. So, and frankly, I don't know the details that much. I know sort of the very basics from a pure math point of view, but if you've heard of the name, Claude Shannon is the main guy about these kind of things. Claude Shannon. Okay. Really interesting stuff. Highly recommend you looking into this. Okay, so that's one example. Okay. It also tells you that, oh, maybe you may want to look into other fields. Depending on the context, it might be more helpful. Okay, that's one example. Going forward, even though we could keep changing the field, let's fix the field to be the reals. Even if you fix the field to be the reals, there are, again, a plethora of very interesting examples. Here's another example. Well, I can look at polynomials, for instance. The collection of polynomials is a vector space. Let's call it P, or maybe curly P. So polys with real coefficients. You could do complex whatever. You could do binary if you wanted. But let's stick to the standard case. So this is a set of all expressions of the form a0 plus a1x plus a2x squared dot 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 a sub n x to the n. Okay. This is also a vector field, vector space. Sorry. Here, n is not fixed, so it could be of arbitrary degree. And the coefficients a0 to an are also not fixed. Okay? You see, this doesn't look like any other vector space we looked at so far. But certainly, if I were to take two such expressions, I could just add them up and scalar multiply. I could do more, of course. I could multiply two polynomials as well. But that is not part of the vector space structure. So P plus Q is a poly. And C times P is a poly, which means this P is a vector space. Okay? Which means you can pretty much import everything that we discussed so far into this context. Of course, the only problem is there's no matrix-matrix multiplication now. Okay? You can do pretty much everything else, though. Does this make sense?
Wait, it's P time or P plus?
P plus Q. If I take two polynomials, add them up.
So Q is also a polynomial.
Yeah, yeah, sure. Yeah. I'm always adding two things of the same type. Yeah. Does this make sense? Yeah.
Why would we not do it where it's like has multiple I guess rows? Because for the binary we did 0, 0, 0, 0, 0, 1. Why would we not do that for like the x's?
Well, x is a variable.
Okay.
X is an independent variable. So you want to leave it as a variable.
Okay.
Yeah. But in a sense, you're pointing to something which is where things get complicated. For now, we're not going to go too much into this. But the idea is, in a sense, if I had an expression like this, insofar as I can keep track of where these coefficients are, meaning what the order of the x is next to ai, well, I can just store this polynomial in one vector in the classical sense. That is true. So this is pretty much the same thing as a0, a1, dot, 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 an. The only problem here is that this n is not fixed. So in this space, there are like different vectors like this of different dimension. So I would need to figure out how to deal with those. Perhaps what you could say is, well, in my application, I'm not going to need any polynomial beyond degree 10,000. So you could just like concatenate, but you don't have to in principle. Very good. Does this kind of make sense? So we'll talk about the correspondence between things like this and this later. For now, I just want to look at P as a vector space. Well, let's think about some linear transformations in this context. For instance, I should ask you, how many of you have seen something called a graph transform? You would take sort of like a function and take the graph and move it sideways and stuff. Okay, that's a linear transformation, in fact. So for instance, what I can do is t, okay, because I know if I were to take a polynomial and shift it sideways, it's still going to be a polynomial. So p of x goes to, let's say this is going to be x minus 1. Okay, this is kind of complicated to parse, but what is this t doing? You feed to it one polynomial. In this world, polynomial is the vector. Feed one polynomial to it, gives you back another polynomial, which is the polynomial whose graph is shifted to the right by 1 unit. Okay, so maybe you can do it like this. T of let's say this is P. This was P, so now something like this is T of P. This is a linear transformation. Linear operator. It's a graph transform. Okay? So for instance, let's be even more specific perhaps. Let's take one polynomial. For instance, consider x squared. X squared, okay, you can imagine it to be this picture. This is one vector in curly P. This is one vector in curly P. In this world of the polynomials, vectors are polynomials are vectors and vice versa. Okay. What is TP? Well, it's going to turn into x minus 1 squared. Okay, it doesn't seem like it's of this form, but you can of course expand. This is x squared minus 2x plus 1. But geometrically, it's easier to think about this, I think, because now instead of having the corner at 0, the corner is at 1, right? So, like this. Make sense? And just to verify that this is a linear transformation, what has to happen? Well, it has to distribute over linear combinations, right? That's always the definition of a linear transformation. So for instance, if I were to take two polynomials, add them up, and then shift, it's the same thing as first shifting both of the polynomials by same unit and then adding. Right? So T P plus Q is the same thing as TP plus TQ. And of course, if I wanted, I could first stretch this graph by some number. So vertical stretch corresponds to scalar multiplication. Well, I could first stretch and then translate, or first translate and then stretch. Okay. Any comments or questions about this so far? So you can import all college algebra into linear algebra, okay, or vice versa, depending on what you want to do. How many of you know some calculus? Just a little bit, okay. Then it's good that differentiation is a linear transformation also. Oop. If I were to take a p, then d of p is nothing but p prime, okay. You can do this more generally, of course, but you know, polynomials, I think it's nice to think about. What does that mean for those of you who don't remember or who haven't seen? Well, there is this like limit definition, whatever, but for polynomials, the rule is very simple. Xn. If you're trying to differentiate a polynomial like this, you look at the exponent of x, you take that exponent, write it as a multiplication, and you lower the index, the exponent by 1. So that this drops, this becomes a1. Here I had a2 x squared, and so on. So for instance, a2x squared now is 2a2x. And then 3a3x squared, and so on. And finally, I'm left with n times a sub n times x sub n minus 1. Differentiation. It's a rule that differentiation is a linear transformation. linear operator. So college algebra is in linear algebra. Calculus is in linear algebra as well, or single variable calculus, but multivariable calculus too, it turns out to be in linear algebra. Let's think about more complicated things. Here's another important example. Space of signals, okay? Discrete time or digital signals. In a textbook, this is denoted by this blackboard S. I'm just going to draw something like a dollar sign. Space of digital signals. Okay, what does that mean? Well, the way I think about it is any vector in S is an infinite ticker tape of numbers. Is a ticker tape of numbers. Is an infinite ticker tape of numbers. Of scalars. Okay, I'll draw a picture in a second. What is a ticker tape? Well, for those of you who are into stocks and whatever, you'll see sort of these like small bands, or even those of you who are not into stocks, every once in a while when you're watching the television, you'd see sort of like numbers sort of passing. You have something like this, okay? And this is like split into little cells. Goes in both directions. Obviously in stocks, it would be only one directional and it would be like finite, but it turns out that for mathy stuff, thinking of this is more convenient. Okay. And I want to think about, so you see I use regularly 1 bars, but to represent the position at time 0, I use 2 bars. So this is my time. 0, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, and so on. In each of these cells, I have one number. Okay? And any such ticker tape is going to be one vector in my space of signals. Why is this called a ticker tape? Because back in the good days, perhaps, when these stocks were being done rather manually, there would be like these like little strips of paper, and it would print out, and there would be a machine, and it would print out the value of a certain stock. Okay? Imagine this machine somewhere here. There's a machine here, and it's like it's printing out this tape. Like this. Dot, dot, dot. And so based on what number you see, oh, number goes up or number goes down. People still use the same idea in a sense, even though currently stocks are being traded so fast that you don't want to be restricted with physical matters. So things are digital now, but even though that is the case, people still use the same notation. And of course, this is nothing but a signal too, from the perspective of digital signal processing. Because when you think about it, everything can be encoded into a sort of strip of numbers, maybe binary, whatever, but let's keep it simple. And essentially, the way I think about it, because I like movies and stuff, I think of this also like a movie strip. Okay, so these are all different scenes and so on. Let's try to give specific examples of vectors in this signal space. So for instance, one signal could be x, the other one is y, let's say. Okay. In fact, I'm going to draw it like this. You can sort of combine, synchronize two signals. Okay. Goes both ways. This is times 0. Say x goes between 1 and 0. 1, 0, 1, 0, like this. And then say y is, at every time it doubles. So 1, 2, 4, 8. In order for this to double, now you need to divide it by 2. 1 over 4, 1 over 2, 1 over 4, 1 over 8, and so on. Okay? So x is an alternating signal, and y is an exponential signal. Doesn't matter what these are called, but good to know. And how do I add these? Well, you're going to take two signals and add the corresponding entries. X plus y is going to be nothing but the signal whose terms are the sums of the terms of x and y. Okay, so for instance, to get the times 0, you add these two, that's a 2. Then it's a 2 again, now it's a 5, now it's an 8. Here it is 1/2. Here it is 5 over 4, here it is 1 over 8, and so on. Okay. Vector space. We can also scalar multiply, of course. Maybe let's scalar multiply x by 3. How does that work? Again, you take this and you scalar multiply each of these entries in the same positions. So 1 becomes 3, 0, 3, 0, and so on. Okay. So you can import all linear algebra, or vice versa, into signal processing. For those of you who like functions and stuff, you can also think of this space of digital signals as the set of all functions from integers into reals. In for mathy language, this is set of all functions from ints to reals. You can also think of it that way as well. Okay? Yeah?
I was going to go back to the polynomial with like the taking the derivative.
Yeah.
How is that a linear operation? Because the way I've understood linear operations is that it preserves the origin, it preserves the distance between like grid lines, so to speak. But like just thinking about derivatives, like does it preserve that, or is there like a different definition of like a linear operator?
No. Let's do it. Very good. So your colleague is questioning this claim I have over here that it's a linear operator. What is the definition of a linear operator? Well, it has to distribute over vector addition. It has to distribute over scalar multiplication. Okay? So if I were to scalar multiply c times a0 plus a1x plus a2x squared plus dot 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 plus a sub n x to the n gets complicated a little bit when you're sort of trying to adapt, thinking about vectors in terms of like tuples as like more complicated vectors, but bear with me. So I'm just going to distribute c times a0 plus c times a1x plus dot 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 plus c times a sub n of times x to the n. Okay. Then I look at the rule. Okay, this drops. This becomes c times a1 plus c times a2 times 2 times x plus dot 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 plus c times a sub n times x to the n minus 1. Okay? And then factor out the c. Two of these plus dot 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 plus n times a sub n times x to the n minus 1. But of course, this is nothing but d applied to the original polynomial. C times d of the polynomial. So at least this d transformation distributes over scalar multiplication. Okay. We also need to verify addition. Continue here. Okay, maybe I'll try to be a little bit more explicit here. Two vectors in P. Say one of them is P, which is of the form a0, a1x plus dot 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 plus a sub n times x to the n. And let's say there's another one, q of x. And let's say its coefficients are bi's. Okay. These are two vectors in curly P. Now, I would like to say the derivative of P plus Q is the same thing as derivative of P plus derivative of Q. Okay. So if I add these two up, that itself is a polynomial. And so maybe I can write it like this. This is a sum polynomial. What is that? Well, I'm just going to add the corresponding entries, and I'm going to sort of collect the terms. And in fact, let me just use a sum notation to be fast. Remember, this was this for loop. I'm saying for I from 0 to n, add all terms of this form, which gives you the sum. Okay. Now, if I were to apply d to it, same rule. I from 1 to n minus 1, or rather n it should be, n ai plus bi I x to the I minus 1. We just drop the exponents by 1, and you take it, put it next to the variable. You don't touch the coefficients. Why do I start with the 1 here? Because if I is 0, this is a 0th term, a0 plus b0. Then I differentiate, that should drop. And so that's the derivative. Okay? On the other hand, dp plus dq, I'm just going to apply the same rule. ai x to the I plus bi x to the I minus 1, I minus 1. But certainly if I were to add these two up, I could just consolidate terms of the same type, and these two should be the same.
So this then is the more like accurate definition of what we're calling a linear transformation, is something that can be distributed over both scalar multiplication and addition?
Yes.
Okay.
Yeah. It's the same thing as saying a linear transformation is something that distributes over linear combinations. Same thing, yeah. Does this make sense? Maybe you've seen the more sort of calculus-looking rule, right? So f plus g prime is the same thing as f prime plus g prime, and then constant times f prime is c times f prime. There's also this product rule, but that is not part of linear algebra. It's more complicated. You also have this rule about what is the derivative of f times g, right? The Leibniz rule, whatever. But that's something more complicated, you see. It's not part of linear algebra. And similarly, even though you could differentiate the product of two polynomials, that is more complicated. That is like a special structure defined for polynomials. So that's the difference, you see. It's like in applications and in different types of, in different corners of math, there are many sort of different vector spaces. But it turns out that depending on the structure of the vector that you're looking into, there might be extra operations that are available to you. And then one of the things you end up doing is, oh, here's my discipline. I don't know. It's like signal processing. Here's my vector space. What are the linear algebra stuff? OK, everything works. And then what are the new things that are applicable only for my specific context? And how do these things operate? So for instance, in the context of signals too, there's something called a convolution. You might have heard of this word elsewhere as well. It's a very important thing. For instance, if you're trying to take an image and blur it out, you would what is called do a Gaussian blur, and that's essentially something like well, it's exactly a convolution. It's a convolution operation. Okay, but these are more complicated things, is what I'm trying to say. Does any of this make sense, or are there any further questions? I realize this is like kind of confusing. I've been trying to prepare you for this a little bit by sort of like talking about matrices as vectors and so on. I was like confusing, oh, what is a vector? What is a matrix? What is a transformation? They're all the same. Like they're all pretty much sort of in your head. I was trying to kind of prepare you for this, but I realized when you first sort of start seeing these kind of things, it gets confusing, disorientating. Okay. Here's a very complicated, or relatively more complicated linear transformation in the world of signals. You take your signal, you apply what is called the Z transform to it. Okay? Because maybe some of you know, in the world of signal processing, there are certain filters. Okay? We'll talk about those later a little bit more, but there are certain filters. And so, for instance, you would like to be able to do something like a high-pass filter. Okay? You take your signal, sequence of numbers like this, you apply something to it such that the frequencies, or rather, only the high frequencies are allowed, low frequencies are sort of gotten rid of. Okay? So for instance, when I'm recording my voice, it's a signal, but there is some noise. Okay? There's some sort of like hum in the background and so on. When I'm editing the video for this class, well, I apply, using DaVinci Resolve, obviously I'm not doing it by hand, but there are like apps, whatever, that takes the signal and sort of gets rid of the components in the signal that corresponds to low frequencies, the background hum. So for instance, coming from the light sources and so on. For that, you use something called the Z transform. Okay, so this is what it does. Okay, take your signal, turn it into a function on, in fact, the complex domain. And in fact, if you take an x, now this is a function of some z, or let's leave it as s, and this is the infinite series x sub n s to the minus n. Okay, you think of this as a function, you say, oh, where does this converge? Where does it diverge? Whatever, and somehow it tells you stuff about the original signal. Okay, I'm out of time. Thank you. We're going to keep working on these kind of things on Monday.